So, let us recap what we did in the previous lecture. By properly doping impurities in a semiconductor, you can make part of it p type and part of it n type. One starts with one variety, the entire wafer is let us say is doped with n type, and then on top of that from one side one makes a more heavy doping of p type, so that the entire thing becomes p type. So, if you have this diagram here, the p-n junction is formed here. From this side the doping is done. First the entire thing is doped with n type, and then from some portion it is made p type, and then you have a junction out here. What we generally show in diagrams in textbooks is this region, kind of this region. So, this is a p type here and then n type here, and then you have a junction in between. This is the junction where this p type and n type overlap. So, it is a kind of a one dimensional diagram. In fact, each line here is a layer. This junction that you are seeing is one layer along which these two things are meeting, and so on. So, this is it. Now, we discussed that when these kind of different layers p type, n type, they meet at each point, you have a lot of concentration gradient. On n side you have lot of electrons, and p side you have lot of holes, and at the junction you have a huge concentration gradient, and because of that some kind of diffusion takes place. And if that diffusion takes place, see, this is our p side, this is our n side, you have lot many holes on p side and few electrons in this. So, here you have NH is much greater than Ne. So, the holes here are majority carriers and electrons here are minority carriers, and on the n side you have Ne much greater than NH, and so electrons are majority carriers and holes are minority carriers, and in this region no holes or electrons are shown, and that is because of that huge concentration gradient which is formed, and holes will diffuse from this left to right in this diagram. So, holes will diffuse like this, electrons will diffuse like this, and therefore, in this region all the electrons which were there and the holes which are coming, they combine and both of these are destroyed. Similarly, in this region lots of electrons are coming from right and the holes are there, and these holes and electrons are combining here, and that makes it carrier free. It becomes carrier free. So, in this middle region you do not have electrons and holes because they recombine with each other. But then in any region new hole electron pairs are created every time. So, recombination takes place in general, and this new hole electron pairs also are generated. So, because of this concentration gradient, because of this diffusion, holes are coming in large number and combining with this thing, but then the new ones are also created, but even they are not present here. Why? We had seen that when it happens in this way, the charge density that gets disturbed. So, if holes are coming from in this figure left to right and they are neutralizing this these electron free electrons here, you have a positive charge appearing here and you get negative charge appearing here. This is because the entire thing was neutral. Remember, this whole p side was neutral, and if holes only are going from here, then what is left here is negative charge, negatively charged ions are not compensated by the corresponding holes, and similarly on this n side you get positive charges, and because the electrons have gone from here, and if electrons have gone from here, then they will leave behind positive charges. So, that creates an electric field, and any whole electron pair that is generated, that is created, that comes up, this electric field will sweep them in respective sides, and this region is carrier free. It is not charge free, it is carrier free. That is the most important point to remember. So, this whole thing is known as a depletion region that we talked. This whole thing is depletion region, and what is depleted? The charge carriers are depleted. You do not have charge carriers. Okay. So, the positive charges which appear in this depletion region and negative charges are appearing in this depletion region on p side, positive charges on n side, and I have shown different widths here. X1 here, let us say this length is x1 and say this length is x2. So, that relates to the doping densities. Okay. So, here you can see that I have drawn purposely large density of holes here, and on this side we have I am showing lower density of electrons here. So, the doping need not be of equal level. Doping of n type and doping of p type can be of different concentrations, and therefore, when holes go and neutralize these electrons, if it is a large density of holes on the p side, then a smaller layer will neutralize a longer layer, because the charge must be same. The charge which is going from positives this p side to this n side and neutralizing. So, what is getting neutralized and what is going to neutralize, that should remain the same, that charge magnitude should remain the same, and therefore, if the hole density is larger here, the width of the depletion layer to the left of this green line will be smaller, x1 will be smaller and x2 will be larger. So, these charges which appear here, they will have their own fields. This region is charge free, here the total, the rho is 0, here the rho is 0, although there are so many electrons, but remember, if there are electrons, there are corresponding ions, positive ions. If there are holes, there are corresponding negative ions, and the rho is 0 charge density in any small region. If you make it is 0, but in depletion region you have charge density which is not 0. Okay, so, this side is x, I am saying this direction is x direction, and remember this is our p side, this is our n side, and this p side extends up to here, remember, and n side extends up to here. Depletion region is depleted of the charge carriers, but all those impurities that we have doped, they are still there. So, the p region and n region still meet at this junction. So, as a function of x, this is the charge density schematically. So, as you go from left to right, the charge density is 0 before the depletion layer, here the charge density is 0. So, you have this 0 coming here, and then when you enter the depletion region, you have negative charge density. So, I am showing this negative charge density by this line here, and well, we have taken a step function type of thing. So, assume that the charge density is constant in this region. So, this is the charge density here, negative charge density, and similarly as you cross that junction, you have this positive charge region here, and that is shown by this line. So, you have positive charge density and then it goes to 0. So, if I say that my depletion layer is of width x1 on the left, x2 on the right, then this point is x equal to minus x 1 and this point is x is equal to x 2. And if this is the kind of charge distribution, and remember these are layers, when I am saying a line, this line is in fact a layer, large layer. So, if you have this kind of charge distribution, then it creates electric field. The electric field will be linear in the two regions. Why do I say it is linear? So, let us calculate it. The charge density, if I plot the charge density rho as a function of x. So, I have a negative charge on this side and positive charge on this side. This is rho equal to minus rho 1, this is rho equal to rho 2. This point is x equal to minus x 1 and this point here is x equal to x 2. This is the depletion region, and I want to calculate the electric field. What is the electric field? So, if I plot electric field as a function of x, how will it look like? So, if I show you the depletion region once again, suppose this is that depletion region and here is that junction which is x is equal to 0 and the charge density is rho which is minus rho 1 this side and this is plus rho 2 this side, and I need a electric field at, let us say, this point here at a distance y. So, what I do? I divide this whole depletion region in different layers. So, let us say at a certain point I draw a line, this is at x, at position x, and then at x plus dx I again draw a line and consider this particular layer. Okay, consider this particular layer. It is positioned at x and its width is dx. Now, this layer you can treat it as a surface charge layer because the thickness is small. So, this layer can be treated as a surface charge layer and the surface charge density, that means charge per unit area of the layer, will be rho times dx. So, you have this sigma, if you write sigma, that will be rho which is minus rho 1 here. So, minus rho 1 times dx, this will be the charge density. What I am doing? I am treating this dx layer as a surface because the thickness is small. So, how much charge per unit area is there, and because of that, what is the electric field at this point in front of the layer? So, if the layer is large, you remember, if you have a charged layer of charge density sigma, surface charge density sigma, and in front of that if you are asking for electric field, that is sigma by 2 epsilon naught if it is vacuum, here it is a silicon crystal. So, that electric field dE1, if I write, that will be minus rho 1 dx over 2 times epsilon. This epsilon is epsilon naught times k, dielectric constant, which is 12 for silicon. So, this is the electric field because of this dx, and then you integrate it, over this whole region here to the left of the junction. What you will get? You will get E1 equal to minus rho 1 over 2 epsilon and then x 1. This dx, when you integrate, it will become this x 1, this length x 1. So, that is E1. What is E1? E1 is the electric field because of this portion, How do I get electric field because of the other portion right of the junction. Let me remove certain part of it. Alright. So, to get the electric field due to the other part, what I am doing now is I am taking a layer here. Once again I take a small layer here to the left of this point where I am calculating the electric field, okay, because of this. At this, again the thickness is dx, this thickness is dx, and remember here rho is rho 2 plus rho 2. So, what is the electric field due to this small layer? That will be dE 2, and that dE 2 is positive charge. So, the electric field is towards right at this point. So, this will be the equivalent surface charge density is rho 2 dx and divided by 2 epsilon, and therefore, E 2 is, what is E 2? I am writing electric field because of this much, it gives me electric field towards right. So, that E 2 will be, this is y. So, rho 2 times y and divided by 2 epsilon, and then I need electric field due to the remaining part which is to the right of that point where I am calculating electric field. So, if you look at that portion, this portion here, and once again if I draw that dx thickness here, this dx thickness here, the charge density, surface charge density is same, equivalent surface charge density, but because of this the electric field here will be towards left. So, it will be in negative x direction. So, if I write that as dE 3, that dE 3 is equal to rho 2 dx, that is the surface charge density, equivalent surface charge density, and then by 2 epsilon with a negative sign. And if you integrate this dx, what you will get? You will get this whole thing is x 2 and minus this y. So, if you integrate, you will get minus rho 2 and then the thickness, and that thickness is x 2 minus y, this divided by 2 epsilon. You have to add all these three to get the final electric field at that particular point, which is at a distance y from the layer, from the junction towards right. So, how much is that? Can we add it? So, E 1 plus E 2 and plus E 3, E is equal to this, and that is minus rho 1 times x 1 divided by 2 epsilon. Let us see if I have written it correctly, E 1 minus rho 1 x 1 by 2 epsilon. So, it is minus rho 1 x 1 by 2 epsilon, correct. Then E 2, let us see what is E 2. E 2 is rho 2 y over 2 epsilon. So, plus rho 2 y over 2 epsilon, and then E 3. What is E 3? E 3 is minus rho 2 by 2 epsilon. Remember x 2 minus y. So, first let me write minus rho 2 by 2 epsilon. So, rho 2 over 2 epsilon with a minus sign, and then you have x 2 minus y, x 2 minus y. Simplify, let me write rho 1 x 1 equal to rho 2 x 2, use this, let me use this, rho 1 x 1 is equal to rho 2 x 2. Remember, the total negative charge on one side, total positive charge on the other side should be the same, so that the total charge is 0. So, I write this as rho 2 x 2, and therefore, rho 2 over 2 epsilon, this much I can take common, then it is minus here, and x2 here, right, minus rho 1 x1 is rho 2 x2 and 2 epsilon. And since I have already taken this common, now this is plus y and this is minus x2 and minus y, which is equal to rho 2 over 2 epsilon, and you see it is minus x2 and minus x2. So, minus 2 times x2, then plus y and plus y. So, 2 times y. So, 2 also I can take common, and then I have y and minus x2. So, that is the electric field at that particular point. So, if you plot this on the graph, if this is my electric field, if this is x, and you plot this part, remember we have done it for x greater than 0 to the right of the junction. So, how will that look like? What is y, by the way? Y is just the distance from the junction. So, you can write it x as a function of x. So, you can also write this as E is equal to 2 rho 2 over, or 2 is not needed in fact, rho 2 over epsilon, and then you have x minus x2. Okay. This y is nothing but that the distance from that junction, which is x equal to 0. So, this point I called it y. So, let us call it x, this is x axis anyway. So, it is this relation which we are plotting. So, at x equal to x2, electric field is 0. So, if this is x2, if this is x2 here, then the electric field here must be 0. If this is x2, the electric field here is 0. And at x equal to 0, what happens? At x equal to 0, if we write at x equal to 0, from this expression, it is minus rho 2 x2 over epsilon, it is negative. So, at x equal to 0, you have this point, you have let us say this point, which is minus rho 2 x2 over epsilon, and then it is linear. You can see that this is a linear equation in x. So, it should be a straight line, it should be linear. And now, the electric field to the left of the junction, you can immediately write from here. It was 0 at x equal to x2, similarly it will become 0 at x equal to x1. And then at x equal to 0, the field has to match, and therefore, that point that I have put there, that will be the field at x equal to 0, and then it should be linear. So, at x equal to x1, this is x1, the field must be 0, and then it should be linear in that region, and therefore, it should be like this. From this side, I have written this as the electric field here. If you do from the left side, you should get minus rho 1 times x1 over epsilon, if the same algebra is done, but then rho 1 x1 is same as rho 2 x2. So, you get this. So, the electric field is linear in the depletion region, right to the junction and left to the junction, they are linear. So, E is rho 2 over epsilon and x minus x2. Just verify, E is equal to rho 2 over epsilon x minus x2. So, this is the electric field in the region x greater than 0. It is like this. What I am going to do now is to calculate potential. So, at the junction, let me take V equal to 0 at the junction. Suppose I take this junction here, and I call this x equal to 0, and let me take V equal to 0 here. You know, we can always take V equal to 0 at our own choice. So, we take this and ask what is the potential in this junction region, depletion region, what is the potential? How do you get this? The basic definition of potential difference is dV is equal to minus E dx, and therefore, it is minus rho 2 by epsilon x minus x 2 dx. This is dV, and if I need the potential, I will integrate this. It is minus rho 2 over epsilon x minus x 2 square divided by 2 plus some constant. And if I am imposing this condition, then 0 becomes minus rho 2 epsilon, x is 0 now. So, x 2 square by 2 plus c. So, that gives me c, and hence what I have is V is equal to minus rho 2 over 2 epsilon and then x minus x 2 square and minus x 2 square. It is quadratic, it is quadratic. So, it varies, it has to be, since field is linear, the potential has to be quadratic. So, if this is x equal to 0, let me plot this V also. If I plot it here, let us say this is now x and this is now V, this was E and this was x. So, what happens at x equal to 0, as you see from this equation, at x equal to 0, V is 0, it should be like that, we have already put that. So, the potential here is 0, and then what is the potential at x equal to x 2, if this is x equal to x 2, what is the potential there? It is rho 2 x 2 square over 2 epsilon. Okay. At x equal to x 2, this goes to 0 and you have rho 2 x 2 square over 2 epsilon. So, here it is somewhere here, let us say, and then it is quadratic. The slope is highest here, electric field magnitude wise it is highest here, and then the magnitude decreases. The slope of this V should decrease in that fashion. So, it should be highest here and then it should decrease and should then it becomes like this. And beyond x 2 what happens? Beyond x 2 electric field is 0. So, V becomes constant. So, even beyond depletion region, if you ask in that p-n junction, it will be like this, constant. And similarly on the other side, and how much is this? How much is this, by the way? This is this rho 2 x 2 square over 2 epsilon naught, 2 epsilon. And on the other side, on the left of the junction, again the similar story, and this will be a constant here. If this is x equal to x 1, let us say if this is x equal to x 1, then it is some value, and then it has to become horizontal like this, and then this side it should be constant. And how much is this? This is rho 1 x 1 square over 2 epsilon. Just like this, this is here it is rho 2 x 2 square, same algebra, everything same, this will be this. How much is the total difference in potential? That total difference in potential will be rho 1 x 1 square plus rho 2 x 2 square and divided by 2 epsilon. So, this is how the potential will vary in this p-n junction. And what about energy? Electron energy. The electron energy will be opposite of this because it is negative charge. The potential energy of electron will be minus E times V. So, the potential energy of the electrons will be going up in this left region, which is the p side, and it will be going down in this right region, which is the n side. So, you had this conduction band minimum here and then the valence band maximum here. Let me draw it for two sides. This is p side, this is n side. You have this conduction band lowest energy, valence band lowest energy like this, but then if that junction is made, if the junction is made, if diffusion is taking place, if the electric field is generated, if the potential has been generated, the potential energies will be changed. And therefore, what will happen? On p side, remember, potential goes down, potential energy goes up for electrons. So, on p side these levels will be raised, on n side the levels will be reduced, and what will you will have is a diagram like this, a diagram like this. This is the conduction and this is that valence band energy. So, the conduction band energies are here, the valence band energies are here, and so on. So, that is how it will look like. This is the n side, this is the p side, and this total difference, this barrier difference, this total difference is what we had calculated, V naught. The barrier, we call it barrier because it opposes the motion of majority charge carriers. Barrier height is V naught, and that we have seen V naught is equal to rho 1 x 1 square divided by 2 epsilon plus rho 2 x 2 square divided by 2 epsilon. So, it is this 1 over 2 epsilon and rho 1 x 1 square plus rho 2 x 2 square. The width, the depletion region width is x 1 plus x 2, that is the width of depletion region. This is x 1 and this is x 2 and this is depletion region. So, x is x 1 plus x 2. And then we have yet another relation, rho 1 x 1 is equal to rho 2 x 2. So, from these three equations eliminate x 1 and x 2 and see what happens. So, from first thing I can rewrite this as V naught is equal to 1 over 2 epsilon, and let me write in terms of rho 2. So, rho 1 x 1 is same as rho 2 x 2. So, I am writing this term here and times x 1, and then I have rho 2 x 2 square, it is this, which is 1 over 2 epsilon, and then you can take rho 2 common and x 2 common, and it is x 1 plus x 2, and that is equal to 1 over 2 epsilon, and then rho 2 and x 2 and capital X. So, this is 1, and then x 2 you can write in terms of x from here. From these two you can write, they are in inverse ratio. So, x 2 will be equal to capital X times rho 1 divided by rho 1 plus rho 2, and x 1, which I do not need actually, will be x rho 2 divided by rho 1 plus rho 2. So, if you add x 2 plus x 1, what you get is capital X, which is here, and if you multiply x 2 by rho 2 here and x 1 by rho 1, you get rho 1 x 1 equal to rho 2 x 2. So, these are the relations. So, let us come back here, your V naught is now 1 over 2 epsilon and then rho 2 and capital X, it is here, and then x 2. For x 2 you have to write this. So, you have another capital X, you have a rho 1 and then divided by rho 1 plus rho 2. So, capital X square is equal to 2 times epsilon times V naught rho 1 plus rho 2, and that divided by rho 1 rho 2. And so, x is equal to square root of 2 times epsilon times V naught and 1 over rho 1 plus 1 over rho 2. So, this rho 1 and rho 2, they are related to the concentrations of impurities that we have put in. After all, how that charge appears in the depletion region? When you have a donor impurity, it comes with one extra electron in the outer orbit, but the whole thing is neutral. So, when this electron diffuses and goes to the other side, what it leaves behind is a positive ion. So, each donor impurity atom gives you one unit of charge, positive charge, and hence the density of charge will be E times the density of these donor impurity atoms in that region, and hence that rho 1 will be just E times that number density of impurity atoms. And same thing happens for that acceptor impurities. On the p side you put acceptor impurities, and these acceptor impurities once again they come with one less electron in the outer orbit, but it is neutral. And so, when this hole migrates to the other side, it leaves behind a negative ion, and therefore, the negative charge which is there in that region will be just E per acceptor impurity, and hence the charge density will be E times the number density of the acceptor ions. So, what you can write? Rho 1 is E times N A acceptor ions density, and rho 2 is E N D donor ion density. So, if you put it here, you get this is square root of 2 epsilon over E V naught. So, it is 1 over N A and plus 1 over N D. So, that is the relation between depletion layer width and the potential barrier here. So, if the potential barrier is high, then the depletion width will be more. If the potential barrier is low, this will be thinner. So, that is how these two are related, and then it depends on the donor ion or acceptor ion densities also. If the semiconductor is heavily doped, so that Na, Nd are large, then this quantity will be small, the depletion layer will be small, and it is understandable. If you have a large doping, if the density is high, the holes here and the electrons here, if the density is too high, only a small layer will be able to create a large amount of field because the charge densities will be large, and therefore, the depletion layer will be small. So, it depends on the concentrations, it depends on the on this width. Now, how the current flows? If there is a potential difference between the p side and n side, is there a current? If there is an electric field, if there is a potential difference, is there a current? It cannot be unless I complete a circuit. Okay. So, if I have this junction, PN junction, and what we are saying is the p side is at a lower potential and n side is at a higher potential. Okay. We had calculated all those things quantitatively, and we have this kind of potential diagram. Okay. The energy diagram for electron is reverse, but this is how. So, this side is at a lower potential and this side is at a higher potential, and the drop of potential is of course only on the depletion region. After that the potential remains constant. So, that means this is at a lower potential, this is at a lower potential, and this is at a higher potential. Now, if I connect these two through some circuit, if I connect this, let us say I put a bulb here and connect it, if there is a potential difference, should there be a current like this and my bulb should glow? It does not happen. Why? Because the junction, when it is prepared for external connections, you have to put some metallic contacts. You have to put some metallic contact somewhere. Okay. So, some metallic contacts you have to put so that it can be joined to the external world. And then just like you had different materials on this side and this side, and it created a potential difference across that junction. Similarly, you have different materials here. On one side you have this semiconductor, on the other side you have this metal. So, there is a potential drop here also, potential difference here also. Similarly, there is a potential difference here also, and when you combine all these things, the three drops, the drop across the junction, the drop across the metal contact here, metal and semiconductor that contact, and here on the right side also you have another metal semiconductor contact. So, when you combine all those things, then the potential here and the potential here again turns out to be the same and no current flows. But inside what happens? Inside this p-n junction, inside this semiconductor, what happens? You do have a potential barrier. If you draw a potential energy diagram, you have just a reflection of this upper one, and it is of this kind. So, this is the potential energy diagram now for electrons. So, if you have electrons which are sitting here, this is my n side, remember. So, I am talking of majority carriers now. If my electrons are sitting here, this is the conduction band energies. If my electrons are sitting here and it tries to come towards this p side, it has to undergo the repulsion from this electric field, and therefore, they will be sent back into n side. Similarly, if holes, for holes the potential energy diagram will be reversed. This will be the potential energy diagram, will be like this. So, if holes try to come from left, once again the electric field will push them back. But then all the electrons are not at the bottom of the conduction energy band. So, some electrons which are at higher energies, they will be able to cross this barrier. So, the conduction electrons which have somewhat higher energy, and why they have higher energy? Because of the thermal energies, because of the temperature. KT is the average exchange of energies and like that. So, if it is higher the temperature, there is a higher probability of populating the higher levels. So, some electrons will always be there in the higher energies in the conduction band, and they should be able to cross this barrier. Electric field will decelerate them, will reduce their kinetic energy, potential energy will increase, but still they will be able to cross, and so the diffusion current is not exactly 0. If these electrons are crossing, that is creating a current in the opposite direction. Similarly, some of the holes can really go from this p side to n side despite of this electric field which is repelling them, which is decreasing this motion. So, you do have some kind of a diffusion current, so we call it diffusion, diffusion current. Majority carriers try to diffuse on the other side because of that concentration gradient, and facing the position of this depletion layer electric field, still some are able to cross, and that creates what we called diffusion current. And this diffusion current is which side to which side? It is from, the direction is from p to n, because these electrons which are trying to diffuse here. So, that will create a current in this direction, and then holes which are trying to diffuse on the n side, that will also create a current in the same direction. So, this is the diffusion current. But how can there be a current if there is no current going in the circuit? How can a current exist across the junction only? So, the other part is, in this depletion region you have electric field, but you also have minority carriers. You also have minority carriers, although this is n type, although there are large number of electrons here, but there are some holes. And similarly, this is p type, and for in this p type also there are some electrons. These are minority carriers. And for the minority carriers, the electric field is all supportive. If it is repelling electron, it will attract hole. If it is repelling hole, it will support this the opposite sign. So, for the minority carriers, this is not a barrier, it is rather electric field which encourages this kind of motion. So, the minority carriers will go, the electrons will go from this side to that side because of this electric field, the holes will go from this side to that side because of the electric field will support that, and this current will be prompted by the electric field, and this is known as drift current. If there are generation of electron hole pair in the depletion region, that will also be swept away, the carriers will be swept away and will contribute to this drift current only in the same direction. And the direction of drift current you can see from this diagram, the holes are going from right to left. So, giving a current in this direction, and electrons are going from left to right, again giving a current in this direction, and this is your drift current. So, the drift current and diffusion current are in opposite direction. Diffusion is because of the majority carriers concentration difference, and the drift is because of the minority carriers because of the electric field existing. And in equilibrium, this diffusion current, the magnitude is same as the drift current, and hence net current is 0. So, this is when we have not added any circuit, we have not added any cell, any battery, any voltage source, any resistance, nothing. This p-n junction is just lying in the almirah. Even then the diffusion current and drift current are going in different directions, the activity is on, it is not idle. Now, the next task is what happens if we connect a battery to it, we apply some voltage to it, which is known as biasing. Okay. So, let us say we have this p-n junction, and this p-n junction the same, this is p type, this is n type, and of course, depletion region and everything, and the metallic contacts here, and we connect a cell to it, and let us connect this cell in this fashion. Let us say some small voltage given here, some V is given here. So, what happens when I connect this external battery here? If you take this n type as the reference, I am raising the potential of this p type by this V. So, this potential which was of this type when there was no battery connected, this was V naught and that was V 1 and so on. This was the potential barrier. In fact, I do not need this line anymore. When I connect this battery of potential difference V here, and if I say that this n side is grounded, so the change is here with respect to this n side. This potential here is raised by this V, and so it will become this. It will become this. also. As a result, this height, this barrier height is now only this much. This is a new barrier height. So, the barrier height is reduced. This is known as forward biasing. Biasing is when you externally you are trying to influence it. You are biasing P region over N region or N region over P region. So, that connecting this battery or connecting this voltage source is known as biasing, and this type of biasing where the positive of battery is connected to the P type and negative is connected to the N type, this is known as forward biasing. And in this forward biasing, what happens? The barrier height, the potential barrier height is decreased. Okay. The potential barrier height is decreased, and also the width of the depletion region also. You remember that width was something like square root of 2 epsilon over E V naught 1 over capital N A plus 1 over capital N D. So, if this barrier height is reduced, depletion region width is also reduced. So, one thing is that height is decreased, and the second thing is that width is also reduced. So, this width, this depletion region width where the electric field exists, that decreases, the height decreases. So, the majority carriers are more than happy, because this they had to cross this depletion region in which this electric field was existing. Now, the depletion region is thinner, and then the total energy difference that was there that they had to surmount, that is also decreased, and therefore, what happens? The diffusion current will increase. Does drift current also increase? Drift current was supported by this electric field. So, whatever minority carrier wanted to come, they were allowed to come. So, even if this support, if this attraction repulsion is increased, that does not actually increase the drift current, because this drift current is decided by the concentration of minority carriers. How many minority carriers are there to take that support? Whereas, for majority carrier it was different. It is not the concentration of majority carriers, but it was going uphill. So, the drift current, which is decided by the concentration of minority carriers, that is not changed because of this biasing. Of course, if you increase the temperature, then that minority carrier concentration will increase, because more whole electron pairs will be there and all those things. So, for a given temperature, this will increase, whereas the drift current will remain the same. So, the net current will increase. In what fashion? Not linearly, because it all depends what is the population of electrons in those higher levels, and that is exponential, that has a more complicated form. So, the current is first it increases very slowly, and then after a certain voltage it increases suddenly, steeply. So, this side is now this battery voltage V, this V that we are putting, that is now this side, and this side is the current. So, in this non-linear way it increases, and the drift current is very small, and that is not affected by this, and that drift current is going like this and remains the same. So, we will stop here and we will take from this point only next lecture.